In this video, we are going to study the factor theorem. The factor theorem's primary use is to relate the relationship between algebraic equations and their graphs. Thus, we are going to factor equations by examining graphs. Start. Here's some stuff that you should already be familiar with. Before we start looking specifically at the factor theorem, we should review the distributive property a little bit. So, evaluate 6 times 98 using the distributive property. This one is centered on the observation that we can rewrite 98 90 plus 8. This is one correct way to use the distributive property. So when we take this, we'd have 6 times 90, which is 540. 6 times 8, which is 48. So we can split this up as 540 plus 48, yielding our answer 588. Example 2. 4 times 1.95, which is really helpful with shopping when you're going to buy 4 of something that's $1.95. Well, in this particular instance, we could write $1.95 as $2 plus a negative 0.05 or subtract 0.05. So 4 times 2 would be $8. 4 times 5 cents is 20 cents. Thus, we would have $8 subtract 20 cents gives you 7/8. Really quick way that you can estimate or get precise value for what you're going to shop. Pre-tax, of course. I'm assuming for people watching the video, this distributive property is familiar. If this is not really familiar, you should stop here and basically go look up and get better at that first. A lot of students are familiar with expanding. A lot of times they'll call it the FOIL method, first, outside, inner, last. And so we've already seen that this is A times C for the first. Outers are A times B. Inners are B times C, and last are B times D. I would like to know, could you create a picture that represents this? What is going on here? Well, each one of these factors, A plus B, we could treat that as a segment length. This is the segment length A plus the segment length B, so we've made it longer. A plus B together. C, then, we could create a rectangle and say, here's our length of C, increased in length by D, so we wind up with C plus D. Well, that whole thing then creates one big rectangle, split up into sections, and the distributive property is telling us we have 2 different ways to calculate the area. One way of calculating the area is just length times width, or alternatively, we can split it up into 4 smaller rectangles and add up the individual rectangles. This one is A times C. Up here, that's A times D. And we'd have B times D, and we would have B times C, which you'll notice that is the 4 areas that we had over here. Just giving us a picture representation, trying to understand the distributive property a little bit better. I would like to make the observation, though, please notice what we have here. When we are multiplying a pair of numbers, a plus b, treating it as a number, we will split it up into two little sections. C plus D will split up into two little sections. That will play a role when we try to investigate the factor theorem. Although you may not realize it, this FOIL method of expanding is actually how we've done normal two-digit multiplication in the past. Let's go through and just do regular multiplication. How do you do 26 times 45? And I swear if I see a calculator, you're going to make me mad.
26.
Well, our standard process was 5 times 6, 30. 5 times 2 plus that 3 is 13. Well, please notice, that was two pieces of multiplication. Progressing over to the 4, we'd have 4 times 6 to give us 24. Carrying over the 2. 4 times 2 is 8, plus 2 gives you 10, which came from two pieces of multiplication. And then we add up those pieces, and we wind up with the answer 1,170. This is an abbreviated way of writing out multiplication. It takes advantage of some shortcuts of the decimal system. We can look at it, though, in an expanded form. 5 times 6 is 30. And this is actually not 5 times 2. It's 5 times 20. Because the 2 is in the tens place, 5 times 2, that's 5 times 20, giving us 100. Please notice those two things in the blue are where we got the 130. When we progress over to the 4, it's not 4 times 6, it's 40 times 6. 40 times 6 is 240. And then when we move on, 4 times 2, it's not 4 times 2, it's 40 times 20, which is 800. And you notice 240 plus 800 is the 1040 that we had before. Well, adding all those things together, we get 1,170.
That's how I do my multiplication. More expanded.
We can see that for many people, they wouldn't want to do it this way because it's more right. Well, this expanded way, please notice what we were saying. 5 times 6 is 30. 20 times 5 is 100. 40 times 6 is 240. 20 times 40 is 800. It's the exact same multiplication in any one of these ways that we were writing it. This abbreviated form that they start teaching you back in elementary school, though, it's just designed to have less writing, which for many kids, somehow they think it's simpler and easier. No matter what, though, they're still doing 4 pieces of multiplication followed by addition. And it's the exact same thing that we would have with variables. B times D, A times D, B times C, and A times C. Those 4 things look familiar? They should. Those are the 4 pieces that we got from FOIL. First, outer, inner, and last. I suggest that you pause the video, and just for the sake of completeness with your notes, you may wish to write these down. I would like to emphasize the main focus of this video is not using factoring. In earlier classes, especially your Algebra 2 classes, you would have spent a lot of time focusing on how to factor. Especially factoring quadratics, you spend a lot of time on in Algebra 1. So these are all formulas that you would have seen before, you would have worked with before. Virtually all of these are Algebra 1 level formulas, and in Algebra 2 you would have emphasized them or got better at working with them. So my expectation is you should be able to recognize and use these patterns even if you don't necessarily have the formulas memorized. You should already have some skill with factoring. Which is why we can look at this particular problem and say factoring. Well, what are you looking for? When you want to factor a quadratic, what are you trying to find? Generally, students remember that you're looking for two numbers that will multiply to give you negative 15, and at the same time, those two numbers are supposed to add up to negative 2. All we're doing is using the problem pattern from number 1. Two numbers that multiply at the back and add up for the middle. Using that problem pattern, can you identify it? Two numbers that multiply to negative 15 and add up to negative 2. Okay, negative, whoa, gotta back that part up. Okay, switch to writing, not erasing. Negative 5 and positive 3. Well, hooray, we found the numbers. What does that do for us then? Remember, factor means to rewrite as an equivalent expression. Rewrite with multiplication something that's equivalent. Specifically, we found these numbers 5 and 3 because we know that they give us negative 5 and they give us positive 3. We have our factors. So let's continue this example. Before we look at solving this, we want to make or emphasize the difference in vocabulary. For some reason, many students tend to think that this distinction isn't important, and they're very, very wrong. There are two important vocabulary words that you need to understand the distinction between them. This first one is an expression. Expressions do not have equals, they don't have less than, it's just a combination of add, subtract, multiply, divide, numbers and letters being put together. An equation must have an equal sign, and for some reason many students seem to not care about that distinction, and so they're not able to pick up on clues in directions because they don't see the vocabulary telling them what they need to do. For this example number 4, we want to solve the equation using the zero product rule. Well, of course, right now we can see that it does not currently fit the zero product rule. But we do have the equals 0 for the zero product rule, but we don't have the blob times blob that we need, which of course is where factoring comes into play. We've already seen problems this year where we could factor this into its equivalent form, creating the blob times blob which we need, and now what? Based on the zero product rule, we know x minus 5 would have to equal 0, or x plus 3 has to equal 0. And for most of the students in the room, you don't even write that step out most of the time. Generally speaking, students just skip to the end and say, x is going to equal 5, or x is going to equal negative 3. And thus we have our solutions. I'd like to look at this in a slightly different way, though. How could we factor using the quadratic formula? Same problem again, so we already know how it's going to factor. But let's pretend for a second that we don't recognize it, or maybe we forgot that factoring technique, or basically we just don't know how to factor. How could you use the quadratic formula to factor? Well, the quadratic formula has the problem pattern ax squared plus bx plus c, but it's not just ax squared plus bx plus c, it's equals 0. So in this instance, we can use the quadratic formula to solve an equation. And once we have the solutions to the equation, we can take those solutions and turn them into factors, which would help us factor the quadratic. Thus, let's run through and use our solution pattern for the quadratic formula. And please tell me what we're going to plug in. X is equal to positive 2 plus or minus the square root of b squared. Negative 2 squared, that is negative 2 times negative 2 gives us positive 4. 4 times a times c, c is negative 15, all over 2 times a. Thus, this would simplify negative 2, not negative 2, it's positive 2. Positive 2 plus or minus the square root of 64 all over 2. Of course, the square root of 64 is just 8. Which would give us, extend the page, 2 plus 8 over 2, or 2 minus 8 over 2. In this instance, on the left, 2 plus 8 is 10. 10 over 2 gives us 5. 2 minus 8 is negative 6. Negative 6 divided by 2 gives you negative 3. And we can see that in the end, we obtain the same solutions that we had previously from the zero product rule. Here's the big thing that I'd like to caution you about. A great many students will make the error of saying, I have positive 5 and I have negative 3. That's not correct. As we will see with the factor theorem coming up, we're doing the example, providing some motivation for the factor theorem. The reality is many students get confused by the letter x. Remember, we've talked all year long that there's a difference between x, the specific number, and x, the placeholder variable. In this particular problem, when we come up to the beginning, if we are trying to solve this equals 0, this is about a specific unknown number, or numbers x. Which specific numbers make it true? And once we go through and get to that point, we have our solutions. But at this stage, we're going to change it so that we're no longer thinking of x as a specific number. We're now changing our thinking so that it's x, the placeholder dummy variable. The reality is, we're not finding specific unknowns here. We're finding constants that are solutions to the general quadratic. You'll see what I mean in greater detail. We'll correctly identify that we should have changed the signs on these, and I will elaborate a little bit further when we get to the factor theorem, okay? Okay, what if we want to use a graph? Factor this graphically. Well, here's what I'd like you to do. Please put this in your calculator, so we'll just save some time and use the y equals feature on our graphing calculators to create the image. And here we have already taken the graph. You can see what I've got here at the y2, x squared minus 2x plus minus 15. I've got entered in. I've graphed it in the standard window, and so we can't see the vertex. We may want to change the window just going downward from the y so we can see the vertex a little bit better. I'm just going to take it down to negative 20 just so we can see. ultimately it's not really important, but it's been my experience that students want to see the whole thing anyway. How can we use the picture to factor? How do we get the picture to find those numbers? Well, the relationship is actually tied right into the quadratic formula. When we were trying to factor based on the quadratic formula, we actually did not factor the expression, we solved the equation. Specifically, we were solving the equation for when the expression equals 0. We will do the same thing with the graph. Where does the graph equal 0? Absolutely, Dylan. It equals 0 where the height is equal to 0, which is where you touch or intersect with the x-axis. Thus, on this one, we're looking at these 2 points and saying those points where we're intersecting the x-axis, that's how we can find the numbers. Of course, we recognize that those numbers are -3 and 5, the same way that we could find the -3 and the 5 by solving with the zero product rule, or we could find the -3 and 5 by using the quadratic formula, or now we can find these numbers by using the graph. It's giving us multiple options. We can use factoring, we can use quadratic formula, we can use the graph, and in any instance, we're searching for these numbers. Well, now that we've found them, we can actually apply the graph and say, because it crossed at -3, we'll switch the sign. And because it switched at +5, we'll switch the sign. And we have our factored form taken from the graph. Not based on a formula, taken from this understanding of graphical. Where this really comes into play is the factor theorem. Now, I suggest that you write them down. You can pause the video if you'd like to hear, but basically, this factor theorem is telling us if you are trying to factor, if you're trying to rewrite your quadratic, you have 3 different ways you can do it. You can use it based on the formula. You can use it based on the quadratic formula, and you can use it based on the graph. All 3 of those are ways of understanding the relationship between factors and solutions. Basically, the factor theorem is telling us a factor is the same thing as a root, which is the same thing as solving p of x equals 0. There are multiple ways of talking about the same thing. I also want to emphasize number 3 here. When we factor these, whether it's quadratic formula, whether it's graphing, whether it's whatever, when we factor them and get 2 solutions, or 2 solutions to the quadratic, p of x equals 0, we will get the form x minus b and x minus c. But what many students will sometimes forget, we can also have a constant. Finding out where it crosses the x-axis will give you the factor x minus b and x minus c. But there is still going to be a vertical stretch, a vertical flip potentially. There's still some sort of vertical component that will tell you about the vertex. In particular, I could draw a quadratic going through these 2 points that has very different behavior. And I could draw another quadratic that would come down and have not the wrong side for what I wanted. They can have very different behavior. In fact, we can even have it change direction. I have a whole bunch of quadratics all going through those same 2 points, those same 2 x-intercepts. So how do we make the distinction then between which of these other graphs we're doing and the specific one in red that we want? This constant k right here is what accomplishes that. The constant number k is going to completely determine what kind of other behavior is going on. The 2 factors will give you where you cross the x-axis, if you even cross the x-axis at all. And the constant of k is what gives you information about the vertex and other locations. So let me clean up the erasing, and if you haven't already finished copying it, go ahead and do it. Okay, so factor. How do you want to do it? Do you want to use a formula? Do you want to use quadratic formula? When I say formula, I mean like the a plus b, a times b stuff. Or do you want to use a graph? We've got our choice.
Graph.
Okay.
Graph.
If we're going to graph, grass. If we're going to graph, we need to put this whole thing in. All right. Having entered our equation in, 3x squared minus 6x minus 72, we can hit the graph button. And I'm using my same window that I had before, and seeing that there's a whole lot of stuff that I can't see. But who cares?
We got what we wanted.
We have what we want. We have where it's crossing the x-axis. So what are the values where it's crossing the x-axis? Here it's crossing at -4, and here it's crossing at +6. So that tells us if x subtract a -4 and x subtract a +6. Well, of course, we know most people don't like writing subtract the -4, and they'd write the subtract the -4 as x plus 4. But this is still incomplete. We are still missing the constant k. Because if we expanded this, if we FOILed it, we'd have x squared minus 2x minus 24. And that's not quite what we had. Unfortunately, getting the constant in this instance is very, very quick, very, very easy. What is the coefficient supposed to be on the x squared? It's supposed to be a 3, so that's our constant. If we were just going to use the distributive property, taking it across, we get exactly what we needed. In fact, the constant k is always going to be the leading coefficient. In the quadratic formula, it's the a in the quadratic formula. Okay, let's continue. Factor it graphically. Sweet. We already did that. It's worth noting another way that we could have done this if we chose not to do it graphically. Grab this stuff. Come on. Grab it. Pull it down. We could have factored out the 3. If you recognize that all 3 of those coefficients, or all 3 of the constant numbers, number parts, had a factor common number 3, if you take out 3, you're left behind with this stuff, and then you're searching for 2 numbers that will multiply to -24 and add up to 2, or add up to -2, and -6, and that's how you would have got it. More than one way to do it. But we already did the graphing factoring graphically, so that's cool. All right, we have 2 last examples to look over. I want an equation. What quadratic has these conditions? It looks tricky, but really it's just straightforward. It's telling us the same kind of information that we would have graphically. P of 4 equals 0, that's telling us it's going through the point 4, 0. That's something on the x-axis, which is telling us that this 4 is the letter C in our factoring. It's not the x. Remember how earlier in the video I was talking, there's a difference between the x and the x as a specific number and x as a general variable? This 4 is not the general variable, it's the specific number. And the specific numbers are the factors that we're using. Having the point P of, having this criteria of P of 4 equals 0 just tells us that we've got a factor. Similarly, having P of negative 2 equals 0, that will give us the factor x subtract a negative 2, which we know is x plus 2. And so we have a factored form. With the issue, we still do not know what this constant k is supposed to be. We don't know the leading coefficient. It's not 7 though. We will use the third criteria though to give us what we'd like. This is telling us if we plug in x equals 1, we get out the image of 7. So if we plug in x is 1 for the specific unknown number 1, it will give us out the image of 7. Well, this isn't so bad. We can solve this equation in the yellow and get our value of k. 1 times 4 is negative 3. 1 minus 2 is negative 1. And when we simplify that, we have 3k equals 7. K has to be equal to 7 over 3. Which is nice because now we can replace the k with the number we know it has to be, and we have our factored form. P of x is equal to all this stuff in the purple. We have an equation. We have the factored form for the quadratic. If we wanted it to expand, we could expand it using FOIL and then combine our like terms, get our cross product term, and put it all together, and we're good to go. Similar problem, just so that you can get a little bit of extra practice with it. Find the quadratic which crosses the x-axis at negative 3, and it crosses the x-axis at 4, and it crosses the y-axis at negative 5. Well, what is this stuff telling you? If it's crossing the x-axis, I kind of wish that I didn't have this racket around now. Well, if it's crossing the x-axis at negative 3 and 4, it's telling us that at negative 3, the height is 0, and at 4, the height is 0. It's just a different way of writing down those criteria that we had before. It's just a different way of telling us, based on the factor theorem, that we have this. We have that factor x plus 3, we have the factor x minus 4. And the only thing that's missing is this k. So just like before, we need to figure out the value of k, which we can do by using the other criteria. If you cross the y-axis at negative 5, what does it tell you? What point is that? -5. So if we plug in the x, we get out the y. So -5 is equal to k times 0 plus 3. Oh, I wrote that one backward. 0 plus 3, 0 minus 4. So -5 is equal to 3 times -4 gives us -12. And so when we divide that out, we get k is equal to 5/12. And so we can come in and replace it now. 5 I wanted that in purple. K is 5/12. And we have a factored form for our quadratic. Thus, we have finished our topic for today. Based on information about the graph, specifically factors, zeros, and roots are really all the same thing. Or rather, they're very intricately related via the factor theorem.